Okay everyone, this is section 7.3. In this section, our goal here is to be able to graph and simplify functions involving the natural base e. The natural base e is what we call the Euler number. So even though it looks like it could be pronounced Euler, it's really called the Euler. Okay, and the history of mathematics is marked by the discovery of special numbers, and we've already talked about I, the number I, and pi. Okay, and another special number is denoted by the letter e, and this number is called the natural base e, or the Euler number. The expression 1 plus 1 over n, all raised to the nth power, approaches e as n increases. So how we could put this in the calculator is if we go and the second button and the ln button, which is below log on the left hand side, is the e. And if we put an exponent of 1 in there, okay, e is approximately 2.718. Okay, so that's our letter e, or the Euler number. Okay, so the natural base e, again, is approximately equal to 2.718 as n approaches positive infinity for 1 plus 1 over n, all raised to the nth power. So this is irrational since it keeps going on forever. And not only can we treat it like a number, we can kind of treat it like a variable and do exponent properties and rules along with it. So if I have the same base of e, or the Euler number, and I'm multiplying them together, again, with exponent rules, I can just simply add together the exponents. So 5 and 2 makes 7. And since it didn't say evaluate, it just said simplify, e to the 7th power is just fine. On b, now we have real number coefficients out front that we can take care of first. So 12 divided by 3 is 4. And then if we look at the Euler number e, well, they're exponents. They're the same base of e. And when we have the same base being divided by each other, all we need to do is subtract the exponents. So 4 minus 3 is just 1. So 4e to the first power. And then the last one, normally we would take the outside exponent and distribute it to the inside stuff. But we got to be careful because, again, it's not 5 times 2. It's 5 exponent 2. And if you don't remember that there's a 1 on the inside as an exponent of 5. And if we distribute that 1 to the 2, or the 2 to the 1, if you want to think about it that way, okay, 2 times 1 is 2, so it becomes 5 squared. And then the e, or the Euler number, base, I need to do negative 3x times 2, which is negative 6x. And some of you guys want to say, well, that's done. Well, we can simplify it a little bit more. I could simplify 5 squared. And that negative exponent, well, that was special. Because we said, well, when we have negative exponents, all we need to do is flip it over. So I know 5 squared is 25. But negative 6x, since it's negative, it's going to flip to the bottom and turn positive. So it's going to be turned to positive 6x. And there we go. So remember, any negative exponents just get flipped to the bottom. Now in example 2, we're going to actually use the calculator to evaluate the Euler numbers with the common exponents or any kind of exponents that's given to you. So in A, we are going to evaluate e to the 4th power. So in the graphing calculator, I need to do second ln button, which is again below the log button. I need to put e to the 4th power, so 4 is the exponent, and let's say to 3 exponents. That should be enough. So 54.598. So about 54.9598. Oops. Okay, and then e to the negative 0.09. I can do that one too. So second ln button, negative 0.09. And again, to 3 decimal places, that'll be 0.914 if we round. So about 0.914. So if it asks you to evaluate the Euler number with a given exponent, all you need to do is put it in the calculator, and about 3 decimal places should be enough. We can also graph these natural base functions. They are still exponential functions, so these can still be growth or decay. So a function in the form of y equals a times the Euler number e to the r times x power is called a natural exponential function. If a is bigger than 0 and r is bigger than 0, the function is an exponential growth function. And if a is greater than 0 and r is less than 0, the function is an exponential decay function, which makes sense because if your rate or r is bigger, it's going to be growing each time. Whereas if your r is less than 0, it's going to be decaying by a certain percentage in time. So in example 3, we're going to graph one of these. So we're going to graph it and then state the domain and range. So first off, let's just try to think about, is this growth or decay, just by looking at the function before we even go graphing. Well, I see the x and my r up here. Okay, since I have a negative in here, it's less than 0 whenever something is negative, so it should be decay. And before we go graphing, it should be falling from left to right. That's what a decay model looks like. So when we go to do our table, we're going to see if our data from our table matches what our picture should look like for when we decay. So I need to put in that function into the graphing calculator into y equals. Okay, so e, so second ln button, raised to negative 0.75 parenthesis x minus 2. And then tab to the right to get out of the exponent because we need the plus 1 on the outside of it. And second graph, and here is our table of values. So as you can see, if we keep going down forever and ever on the x-axis positively, it's approaching 1, so that's our asymptote. So 1's our asymptote, and if we just stick to, let's say, negative 2 to 3, that should be enough points. So negative 2, negative 1, 0, 1, 2, 3. So if we fill out the y column, well, negative 2 was 21.086, negative 1 it was 10.488, 0 it was 5.482, at 1 it was 3.117, at 2 it was 2, and at 3 it was 1.472. And if we go graphing this, well, negative 2, 21 is clear off the graph, and that's okay. Okay, so at negative 2, we'll just put a dot up here somewhere to represent 21. And then, if I make, let's say, each unit 2 on this graph, 2, 4, 6, 8, 10, at negative 1, which would make this be about 21, let's say. So you can erase this one up here. If we make our units worth 2. Then, at 0 it was 5. So right in here somewhere. And again, it's not going to be perfect. Then, at 1 it was 3. At 2 it was 2. At 3 it was almost 1.5. And it's getting very, very close to 1. So that was our asymptote. Okay, so the asymptote is 1. It's getting approachingly, or very, very close to 1. So it's approaching 1. So there's our graph of decay, and it does match decay because it's going down from left to right at a very, very quick pace or at time. Okay, so the domain, if we think about that, That's all the x's. Well, we're going to hit all of them. We're going to hit all the negatives and the positives. So that's from negative infinity to regular infinity, or all real numbers. But the range, we're only hitting everything above 1. So y is greater than 1. And again, it's not equal to 1 because we're not going to actually cross y equals 1. Okay, so it's everything greater than 1 on the y's. In example 4, the length L in centimeters of a tiger shark can be modeled by the function here. L equals 337 minus 276 times e to the negative 0.178t, where t is the shark's age in years. We're going to graph the model in the graphing calculator, and then use the graph to estimate the length of a tiger shark that is 3 years old. So let's start by going to y equals and putting in that function. So 337 minus 276, not y equals, there we go. So 337 minus 276, second ln button to make the e, negative 0.178, and then t, we're just going to put the x in there. Now, instead of making a table of values, we're just going to hit graph, just right off the bat. Okay, and if we try to find the calculation of when that tiger shark is 3 years old, or when x equals 3, let's hit second calc, or second trace, and we're going to go down to find the value, so you can hit enter on that. So when x is 3, okay, so when x is 3, in the bottom left corner of my screen there, when it says plots, and below that it says x equals 3, okay, y1, it says it's 175.19, okay, so that length in centimeters of a tiger shark is about 175 centimeters. So 175 centimeters, and we use the graphing calculator to calculate that value from its graph. And one of the last things we're going to talk about in this section is compound interest, but compounded continuously. In the first section, we talked about compounded interest at a specified interval in a year, like monthly, yearly, quarterly. Okay, this is compounded continuously, so it's a little bit different formula. But P is still the principal in this, and A equals P times E to the rate times time. Okay, time is still in years, but the rate is still expressed as a decimal. So we're still used to moving the decimal point 2 places to the left in order to make the percentage into a decimal. So in our last example here, you deposit $4,000 into an account that pays 6% annual interest compounded continuously. So this tells me I need the compound interest continuously formula. And to the R times T. So what is the balance after 1 year? So we're finding the amount, but the principal is $4,000 times E to the rate, but 6% as a decimal. Put it on the end and move it 2 places. So it's 0.06. And then for 1 year, so T is 1. So we're going to put this in the calculator and see what we get after 1 year, and that's going to be our balance. So hit second quit to get it out of the graph if you're still in that mode. But $4,000, and then second ln button to make the E, 0.06 times 1 for 6%. And in 1 year, compounded continuously at 6%, we have now gotten an amount of $4,247.35 if we round. So again, we're working in money, so label it money. Don't leave that off of there. $4,247.35 when we round.